Hey YouTube, welcome back to my data structures in Typescript series. In this video, we're going to go over the implementation for a binary heap, and the implementation that we're going to go over specifically for the binary heap is the minimum binary heap. You can implement a max binary heap by just kind of doing the opposite I'm doing when comparing elements, and yeah, let's hop right into it. So we have the description. A min binary heap implements the priority queue abstract data type, and it has constant access to the minimum element of the heap. I don't know why I said this. So when we add and remove elements, we're going to get logarithmic time operations because of the complete binary tree invariant. And then peaking at the minimum element is going to be constant time because we have access to the root of the element. So let's hop into the definition of the binary heap class. The class is going to take a generic type T to hold our elements, and it has two instance variables. We're going to have a heap, which is a generic type T array, a dynamic array to hold our elements, and this is going to be the tree representation of our heap. And then we're also going to take in a compare function, which is just a type that I have right here. And then the constructor is going to take in an optional parameter with elements, which is an iterable T. And it's also going to take an optional parameter, which is a compare function. And this is because, well, first, the elements is optional because we can first construct an empty heap without anything being provided to us by the client. And the second optional parameter compare function is only needed when the client is using objects that are a bit more complex than basic primitives, and we can't use our default comparator. So the constructor is just going to initialize the heap compare function, the compare instance variable, to the compare function if it exists. Otherwise, we're going to use our default compare, which is just the triple equal signs in JavaScript. And then if they provide us the elements to construct the heap from, we're going to set this heap equals array.from. And array.from is a helper which takes in an iterable, and we can pass elements because that's an iterable type. And then we're going to call this dot heapify, which is just going to heapify the heap. And this is going to run in O of n time, which we'll get into right now. So what the heapify does is it loops through what you might think at first to make this array into a binary heap is to take every element and insert it into a binary heap. So you're enqueuing the elements one by one from the supplied elements into a binary heap, and then you might think that the resulting time is going to be n log n because for each element in the array we have to enqueue, which is a log n operation. But there's this actually neat trick called Heapify, which does the same thing but only in a linear amount of time building the heap. And what's happening is we're taking the array, and you can think of the representative tree, and we're only going to sync elements starting from the second last row, because we don't need to sync any of the elements in the last row because those are already child elements, right? So because we are skipping the last row, that's already half of the elements in the tree, and as a result, it is a linear operation. I'll have a link to a paper you can read in the source code, which will be probably right here, and I'll also link that in the description below. So what we're going to do is set this pointer I equal to the maximum of two variables, either 0 or the floor of this dot size divided by 2, and then subtract 1 from it because that is the index. That's like the index. This is the index that's pointing at the element that's at the half of the array, but we have to subtract 1 because there's the root element starting off with. So this is just the formula to get the index. And then what we do is, as long as we're going to skip this because we initialized I just initialized in the line above for readability. As long as I is positive, and we're going to decrement I each time, we're going to just call this dot sync at the index I, and we'll implement this later. So yeah. So again, you might think this is n log n time because this is looping through half of the array, and this is taken log n time, but with an actual analysis that I don't know on the top of my head, this is a linear operation. So this method size returns the size number, returns the size of the heap, and it runs in constant time because all we're doing is just returning this dot heap dot length. And then is empty, this method returns a boolean true if the heap is empty and false otherwise. What we're going to do is just return this dot size equals 0, check to see if that's equal to 0. So those were our niceties. The next set of methods that we have is insertion. So what the add method does is it takes an element type t and it doesn't return anything. It's just going to add to the heap, and this runs in log n time. So the way we do this is we first, if you remember, when we insert an element, we have to insert it at the bottom right of the tree and then swim it up so the heap invariant is satisfied. So what we do is we push it to the end of our array. We're going to push element, and then we're going to get the index of the last element. So for readability sakes, I'm just going to put that into a variable. So index of last element. Then we're going to just do this dot size -1. And then we are going to simply swim the element, the last element up, and then swim, you can see from the description, takes an index k, and it swims an element with index k until the heap invariant is satisfied, and this takes log n time. So we're just going to pass in the index of the last element, and this is going to swim it up. And of course, this takes O of log n time, and that's why add is log n. The next set of methods are our accessing methods, and we have just one, peek, which returns type t or null, and this peeks the topmost element in the heap. So if our heap is empty, which we'll know by our method called this.empty, we'll just return null. Otherwise, we will return the first element in our heap array. So return this.heap at the 0th index, and we're good. This next method, which is part of the searching methods, it called contains, and it takes an element with type t and returns a boolean, and this boolean is true if this element is in our heap and false otherwise. So we have to do a linear search, and this is O of n. In our index priority queue, which we'll cover in the next video, we can get this down to constant time, which is cool. But for this, we're just going to keep with a linear amount time, and we're going to return if this.heap.includes the element. So includes is going to check to see if this element is in this array, and it's going to run in O of n time because we have to walk through the entire array potentially. And that's searching, that's contains. So the next three methods are part of our deletion. The first method here, pull, just removes and returns the topmost element of the heap, which is going to be the smallest element since this is a minimum binary heap, and to return t or null depending if the heap is empty. So if this heap is empty, then we're going to return null, and otherwise we're going to call this method called this.remove at, and we're going to pass in the index 0. The reason why I decided to use remove at is because the remove at is going to be used also in remove, which removes any element passed in with the search criteria. So since both methods, pull and remove, are removing, I abstracted that out into the method. So we'll go over that soon. The next method, remove, is a more specific version of deletion, and this takes in an element with type t and returns a boolean. And if it returns successfully, if it removes the element successfully, it's going to return true and false otherwise. So we first need to find the element index of the element if it exists, and if it does, we are going to pass that in to remove at. So we essentially have to find it first, and then we can delete the specific element at that index. So I'm going to say const element index is equal to this.heap, and the array has a method called find index. And what find index, this method is going to take a callback function, and it's a predicate. It's going to take in a value, and then we can return some sort of boolean, and if the boolean returns true, then it's going to return that index for the entire method call. So I'll say, let's say since our heap starts with h, I'll say h, and it's going to be a type t, and then we're just going to return this.compare with the h value. So I'm just going to zoom out for 1 second, the h value and our element, and we're going to return if this equals 0. Because if it's 0, that means the two elements are the same. And I don't need this returns right here. So again, what this is doing is this find index is calling this callback for each element in the array, and this gets access to the element, and then we're just going to check to see if this.compare h and elements is equal to 0. And the reason why we have this is because the client supplied this to us in case the type t is some sort of complex object that we can't just write the triple equal signs to compare. And then if the element index is equal to -1, then we are going to return false because there's no way we can remove something that doesn't even exist. Otherwise, we're going to return this.remove at, and then we're going to pass in the element index. And we're not going to return that, we're just going to call that, and then we're going to return true. and then we're good to go. So the next three methods are our helpers, and these are private because we're not exposing them to the client, and these are our bread and butter methods for the binary heap. We have syncing, swimming, and removing at. So the first method we're going to go into is syncing, and this syncs an element with the index k until the heap invariant is satisfied. And this is going to run in log n time because we potentially have to sync an element throughout the entire height of the tree. But because the tree again is complete, we're guaranteed that the height of the tree is logarithmic. So it's going to take in a parameter k, which is a type number, which is the index, and it's not going to return anything. So we're going to have a loop while true, and we're going to have to do a few steps. The first thing we're going to have to do is get the smallest child, right? Because we need, since this is a min heap, we need the smallest child. So when we swap, the heap invariant is still satisfied. If we take the greater child, then in the previous video you saw that the heap invariant won't be satisfied. So we want to get the smallest child. Then we want to make sure that the smallest child, so here this is going to be index. We want to make sure the smallest child index is not out of bounds. We're going to do those calculations that we saw in the previous video with the child index, and because we're dealing with an array, there's a potential for it to be out of bounds. So we have to make sure the child index is not out of bounds, and then if it is not, then swap it. Then swap the current node with the child, and then repeat, right? So here, we're just going to have I already have it, while true, we're going to get the smallest child index. So we're going to get the left child index, and we have a method here called get left child index, which we'll implement soon. And then likewise, we can say the same thing for the right child index, and put this to right child index. So then let's find the smallest child out of the two. So because the indices might be out of bounds, we have to be a bit careful. So let's assume that the smallest child index is the left child index to start off with. And here I forgot to pass in k because the methods need to know which index it's getting the children for. And then here we're going to make a boolean, and that boolean is going to represent if the right child is smaller than the left child. So is right child smaller than left? And what we're going to do is we're going to first make sure that the right child index is in bounds. So we have to be careful with this. Right child index is less than this dot size. And then the other side of the Boolean expression is going to check to see if the right child index is smaller than the left child index with a method that we're going to implement later called this.less. So this is going to check if the right child index is less than the left child index. And it's going to be the second line. Great. And then if the right child is smaller than the left, then we're going to reassign the smallest child index to the right child index. So the reason why I have these long variable names is because that's cleaner code. If I didn't put this in and I just put this Boolean expression right in here, then I would have to probably use some comments, and using comments aren't the best because they can get out of sync with your code. So this is kind of like a clean code thing, like naming your variables, being very explicit, and also since the purpose of this video is for educational purposes, I'm being pretty explicit with my variable names. So then the second step, we have to do two things. We're going to break. Our break condition is if the children are out of bounds. So that means we've synced throughout the entire tree, and then now we're trying to sync like null nodes, which we can't do. Or if we've synced to a point where the current node at k is good. We satisfy the heap invariant if it's smaller than all of its children. So what we're going to do is check to see if children are out of bounds or element is less than children. And then if it is, we're just going to call break. And then we're going to construct these two booleans. Children are out of bounds. And for the children out of bounds, we can just check to see if the left child index is greater than or equal to this dot size. We can check the left child index because the left child index will be smaller than the right child index. So we're going to check that first. If we check the right child index, the left child index, yeah, like it just doesn't make sense. It just makes more sense to do left child because it occurs first in the array. And then we're going to get element is less and this is not lining up. If const element is less than children, it's just going to call this dot less on k, and then it's going to call the smallest child index. So again, this is for the probably not the first iteration of the loop, but the like some kth iteration of, or not, I won't use k because it's confusing. If like some jth operation of the loop is satisfies the heap invariant, then one of these two will catch true and then will break. Otherwise, we're going to swap the elements at k and then smallest child index. And then we want k to, since we're syncing down, we want k to now point down to where it's swapped before, because now k is still pointing at that parent node, but we swapped the values. So we'll set k equal to the smallest child index. And then we will repeat and go back up. So this is sync. The next method, swim, is much more easier than sync. And this is because we don't have to do any comparisons with our two children. We only have one parent, and we're only going to swim up if our parent is greater than our child. So this swims an element with the index k until the heap invariant is satisfied in log n time. And log n time is the worst case because we potentially have to swim the element up the entire tree. So this is going to take a parameter k, which represents the index of what we're swimming up, and it's not going to return anything. So we're going to get the parent index with a helper, which we'll implement. So we're going to get this dot get parent index. And then we're going to have another loop while true. And of course, we have to pass in the element that we want the parent index of. And then while true, sorry, not while is true. Sorry, and we're not going to do this true. We're going to say while k is positive, because we're going to be decrementing k each time because we're swimming up the tree, which means going back, decreasing the pointer in the array. And we're also going to add another branch to this Boolean expression and make sure that the current element is less than the parent. So with this dot less, and we're going to pass in k and parent index as arguments. So then we're going to do this dot swap. We're going to swap k. We're going to swap the values, the priorities at k and parent index, and then we're going to now move the k pointer up. Not my volume up, the pointer up. And then we're going to set this again to this dot get parent index k. And there you go, swim. It's log n time, and it's much more simple to implement because we don't have to do this comparison to grab the smallest child. All we have to do is just check to see if the parent is greater than the current element, then all we do is swap. So the next method, remove at, is going to be the method that calls sync. And remove at is, if you remember, is called from the pull and remove methods. So this removes the element at the provided index by swapping it with the last element, and then heapifying the swapped element by syncing/swimming it up or down. And it's going to take log n time again. The reason why it takes log n time is because in the worst case we have to sync or swim the element throughout the entire tree. So the first thing that we're going to do is grab the element at the specified index and save it for later so we can return. And then the second thing is we're going to swap the element with the last element in our heap. And this is because we need to maintain that structure property, that complete binary tree, but now potentially the heap property is being violated, so now we have to potentially sync/swim it. So if the element is actually the last element, if the last element in the heap is being removed, we don't have to do any syncing or swimming or heapifying. So we're going to check that, and then if it is indeed the fact, then we're just going to return because we don't want to do anything. So if the element we're removing is the last element in the heap, then just return that now. Otherwise, oh no, my prettifier did those things. Otherwise, we are going to try heapifying. Not try, we are going to heapify. And then we will finally return the saved value of the removed element. So the first thing we're going to do is save the removed value by grabbing it. So this dot heap at index to remove. And then we are going to swap the element with the last element in our heap. So we will, just for readability, clean code sake, do index of last element. And this is going to be this dot size -1. And then we are going to swap the index to remove with the index of the last element. And then we will finally delete the element from our heap. So we'll do this.heap.pop. So then we are going to do if the last element is being removed, then we are just going to return the removed value, and we don't want to sink or swim an element at an index that doesn't exist anymore because we just popped it off. There's no swapping that we ever did. And the way we build this Boolean variable is last element being removed is just checking to see if the index to remove is equal to the index of the last element. There we go. And then if not, then we enter this state of the code, this branch of the code, and we're gonna heapify. Well, first we're gonna try sinking, and if that didn't work, then we're gonna try swimming. So we're going to call this .sink, and we're gonna call it on the element to be heapified, index to be heapified, and then we will try swimming. So we'll know to try swimming if sinking didn't work, and the way we're going to figure that out is to check if the element did not move. So if the element at the index to be heapified is equal to the element to be heapified, and we're going to save that in a bit, then what we're going to do is call this dot swim on the index to be heapified. So here, there's a lot of variables. The index to be heapified, again, is just the index to remove. So we're just like renaming it to, we're just aliasing it for readability sake. And then the element to be heapified is equal to this dot heap at the index to be heapified. So then we save these two, try syncing, and then if it didn't move, and actually we can rename this clean code if element did not move is equal to this. If element did not move, then we're going to call swim. Then after we try syncing and swimming, our heap invariant will be guaranteed to be now resolved again, and then we can finally return our removed value. So just a quick overview of the remove at method, which is a bit longer. We grab the element at the specific index that the client gives us. We swap it with the last element in our heap to maintain the complete binary tree invariant. And then we check to see if that element was actually the last element. And if so, we're not going to try heapifying because we've already removed it with this dot pop. Otherwise, we did actually do a swap and we have to heapify the new element to maintain our heap invariant. So we try syncing, and then if that doesn't work, then we try swimming. And finally, number 5, we return the removed value. Awesome. And then here we have our methods that are leveraged with these major three, sync, swim, and remove at. And these are quite easy: get left child index, get right child index, and get parent index. So get left child index, self-explanatory. It gets the left child for the element at the parent index, and this is going to return parent index times 2 minus 1. And then the right child is going to return that plus 2. And then get parent index is going to take the child index. We're going to divide that by 2. And then we're going to take the child index, subtract that by 1, and then divide everything by 2. And then take the floor of that and return that. That's the parent index. Less method, which has been leveraged and used above, returns true if a is less than b and false otherwise. And this is going to use our compare function. And the compare function is going to return a negative number if a is less than b. So this dot compare, is that right? Yeah, a, b is less than 0. And yeah, that will work. Whoops, it's not going to work because we are taking in numbers. We have to pass in the generic type t that they pass. These are indices. We have to index into our array. Great, that's going to work. And then swap is your canonical swap two variables in any programming language. It's going to take two indices I and j. We're going to take a temp variable and swap and then store I, and then we're going to do this dot heap at I is equal to this dot heap at j. Overwrite it, and then since we've saved the I variable, we can place that in the j index. And great, that's going to work. So that was it. That was the binary heap. This is the longest implementation so far in the series, and it's only going to get longer because the data structures are only going to get more complex. Yeah, I hope you enjoyed. I hope you learned a lot. I know I wish I had someone walking me through these implementations when I started out. And yeah, I'll see you in the next video where we'll talk about an improved version of the binary heap where we'll get logarithmic time removals instead of searching for this, O of n, and logarithmic or constant time contains with storing key value pairs in our binary heaps with index binary heaps. Yeah, I'll see you then. Exciting stuff. See ya. Bye.